Okay, recording is on. Class is officially started. I guess I should say, ladies and gentlemen, and Ellie. Okay, good. All right. So before we start class, did anybody have any questions about anything in general?
I had a question about the quiz.
You have a question about the quiz? Okay.
Yeah.
All right, well, I'm going to be going over the quiz in just a second. So when we get to the problem that you have the quiz on, can we talk about it then, or is it a more general
Oh, yeah,
question?
no, that's totally fine.
Okay. All right, yeah, I'm going to go over all the quiz questions like I usually do. Okay, and you guys have all got the news that we're going to be doing this through the end of the year now. And so at some point, you're going to have to stop by the school to drop off your physics book, but don't do it too soon because you're going to need it. We're going to be using the physics book up until very close to the very end of the school year. So don't go dropping your physics book off just yet. Okay, so here is the quiz. So the frequency of an X-ray, well, that one, just look it up in your book, okay? Page 708. Make sure that you put a bookmark or something there, because that chart that you see on 708, you will be needing that chart for sure on next week's test. Okay, so Ian is asking, if we had one of those that were falling apart, do you still need to turn in? Well, when you checked it out, or let me rephrase that, at the very beginning of the school year, some of you took books that were falling apart, and I didn't even bother to write down that you took it because I did not expect to ever give it back. But others of you that took good quality books, those I did write down your name, and I wrote down the book number, so those I do expect to get back. Okay, so Ian, in answer to your question, if I didn't write down the book number, you can keep it. Although if you're not going to use it, if you have no intention of ever using it, then it would be nice to bring it back, even if it's one of the ones that's falling apart, because next year somebody else might appreciate taking it. Okay. All right, so question number one, I'm assuming everybody's good, no questions. Let's go to question number two. Okay, so how do microwaves heat food? Well, it's all due to resonance. Okay, it's like the Tacoma Narrows Bridge, right? Here's the bridge. If you hit it at a frequency that is different from its natural frequency, you can hit it all day and nothing's interesting is going to happen. But if you happen to hit it exactly at the same frequency that matches its natural frequency, then it's going to go crazy. It's going to vibrate like nuts. And if it's a water molecule, then it's going to get really, really hot. But the other molecules will not. It will only be the water molecules that get hot. Okay. Question number three. So we're going to take a wire, we're going to hook it up to the battery, we're going to flip it back and forth. We're going to do this 105.1 million times per second. So that's 101.5 megahertz. And so what type of radio wave is that? Well, that's I hate it when I do that. What type of electromagnetic wave is that? That's a radio wave.
So this is the one I had a question on, Mr. Hendricks.
Okay. Go ahead.
Because it's million, it's billions, right?
Well,
Or sorry, it's 10 to the 6th, right? It's millions.
Yeah, right. So 101.5 would be 1.05 times 10 to the 8th.
Okay, yeah, 10 to the 8th.
Yeah.
Oh, never mind. I see my problem now.
Okay, yeah. So when I look on the chart, 10 to the 8th, yeah, that's very definitely down in the radio part of the spectrum. I'm looking at this chart.
Yeah, I
right
was
here.
thinking it was a billion and it was on the line, but that was
Okay.
just a small mistake.
Okay, yeah, that's the easy mistake to make. Careful about that next week. Don't make that mistake next week. Okay, question number 4. Okay, so speaking of next week, when we take the test next week, okay, let's go over each one of these because it's important. So if you give or receive help from any person while taking the test, that is most definitely cheating, okay? And serious cheating, I mean like big time. the kind of stuff you can get an F for in the class. Okay, so you are in fact allowed to use the book, the internet, any other non-human resource, you are free to use it. But be careful, I'm going to do it the same way this time that I did last time. I have purposely designed the test so that, or actually I'm still in the process of writing the test, but I am purposely designing the test so that it can only be done in 90 minutes if you don't waste time looking stuff up on the internet. Okay, so if you're going to take the time to look stuff up on the internet, then you're going to run out of time. Okay, so do not rely on the internet. I see your questions. I'll get to you in just a sec. Okay, so what will it cover? Yes, this is what it'll cover. Okay, so the only one of these statements that's false is the last one. You are not allowed to take it whenever you want. Okay, there is a time window. So it's going to be on Friday from 1 o'clock until 2:30. Well, actually, I think I'm going to stretch it out. I'm going to give you from 1 until 3. I'm going to give you 2 hours. And you have to do it during that window. So make sure that you coordinate with your brothers and sisters or parents or anybody who needs to be using the computer so that you have exclusive use of the computer during that 2-hour block. Okay, so Anna is asking how do derivations work. So what I think I'm going to do is I'm going to give the test in 2 parts. So part 1 is going to be multiple choice, and that'll be 1 Canvas assignment. If you've looked on Canvas, you've seen that I've already reserved space for them. Okay, so part 1 is going to be multiple choice, and so you just click on the right one and answer in Canvas. Part 2, I'm thinking, is going to be free response. So in that one, you're going to have to write out your answers, and if you prefer to write them on paper and take a photograph and then upload the photograph, that would be okay. So if that's your plan, I would recommend that you have a camera right by your side there. But I will also allow you to type them into the text box. Okay, so Maddie's asking if it's about as long as the last one, and the answer is yeah, it will be about as long. I am giving you a little extra time, but not much. So it's basically about as long as last time. Yazin is asking about partial credit. So yes, and that's exactly the reason why I'm doing it in 2 parts. So on part 1, multiple choice, you do not get partial credit. If you don't get it right, you miss it all. But on part 2, the free response ones, that's where you're either going to do it on paper and take a photograph of it, or you're going to type it out. On those ones, I will give partial credit. Yeah, good enough. Okay, so which ones should you reserve more time for? Probably the free response ones. I think that the multiple choice questions should be pretty quick. And then Zach's question will be designed in a similar way. So hopefully, as Zach, I've just answered your question. Okay, so we'll talk more about it later, but yeah, now's a good time. Anybody else have any questions about the test next week? Okay, so let's go on to the very last question, which was the secret word, which was not really a word, but hey, that's okay. There's no law that says the secret word has to be an actual word. In fact, tell you what, while we're thinking about it, I know Jaron doesn't like saving the secret word for the end. Let's do one right now. Anybody want to suggest a secret word for today? Or phrase or anything like that? Oh, you were disappointed to see that I didn't put ooh on there. Yeah, sorry, I kind of forgot about that. Pizza mozzarella. Okay, Bridget, I see you've got your hand raised. So Bridget, go ahead and type something in or turn on your mic. Oh, there's a mistake. Okay, all right, I won't write it. Okay, so pizza mozzarella was the first one that I saw. So let's just go with pizza. All right. So there you go. That's the secret word for today, pizza. Okay. All right, let's get on to the rest of the stuff. Oh, I'm glad I put this in here because I would have forgotten. It has come to my attention that some of you have figured out something, but others of you have not figured it out. So as you can see on the screen here, you know how it is that I allow you to retake quizzes. Okay, and back if we were at school, you would come in before school or during lunch or whatever and retake the quizzes. That doesn't work so well now. So what I have done is I have set the quizzes, I have set the quiz features on Canvas so you can retake the quiz as many times as you want. Okay, and so some of you have figured that out, and you've just kept on retaking the quizzes until you get a perfect score, and I'm okay with that. Okay. As others of you haven't figured that out, and I probably should have explicitly said it. I thought it would be obvious, but I guess it wasn't. So those of you that don't have very good quiz scores, just open up Canvas and retake it. But now this is really important. So look down here, the part that's in yellow. This is really, really important. I do not have Canvas set up so that it automatically updates SIS for a lot of reasons, one of which is I just don't fully trust Canvas. And it's not just me. Some of the other teachers have mentioned they are seeing some similar weird things, kind of like the problem that we had with our last test. I'm not the only teacher that's seeing that, so I don't fully trust Canvas. Okay, so I do not have the grades automatically transferred from Canvas to SIS. I do that manually. So what I do is after the due date and the due time for a quiz has passed, I go in and I look at your scores and I transfer them manually into SIS, which is also Aspire. When I say SIS, I mean Aspire, okay? It has two names. Okay, so now, those of you that want to retake old quizzes where the deadline has passed, well, you can still do that. But I won't know that you've done that unless you tell me. Okay, so make sure you send me an email and say, hey, Mr. Hendricks, I retook quiz such and such. Okay, and so if you do that, then I will manually transfer it into SIS. But if you don't tell me, I won't know. Okay, make sense? Okay, now before we talk about the homework last time, there are a couple things that I didn't say last time. I figured that you would read the book, and you guys, especially now, you have got to get in the habit of reading the book, and don't rely on the teacher to give you all of to spoon feed you all the information. Don't rely on that. Okay, so on page 706, some of you may have noticed that they say that the speed of an electromagnetic wave traveling in air is c. But then and hopefully some of you said, wait a minute, I'm not sure I believe that. And then when you get to page 707, you'll see that they contradicted themselves. On page 707, they say that air is a material type known as dielectric, and the velocity of an electromagnetic wave traveling through a dielectric is less than it is in vacuum. So they completely contradict what they said on the previous page. But hopefully you guys already knew that. But it turns out that if all you want is 2 or 3 sig figs, the difference is so small that you can ignore it. But if you do go out to the 5th sig fig, then you will see that the speed of a wave, electromagnetic wave in air, is in fact a little bit slower than it is in vacuum. Okay, and then the other thing that I didn't specify last time, but I'm trusting that you figured out, is they've got this equation here. They say V is equal to C over the square root of K, and I'm hoping that some of you said, hey, wait a minute, that sounds awful familiar. Didn't we have something like that before? And the answer is yes, we did. The refractive index. So this K value that they give you, which by the way, technically, that K is supposed to be a Greek letter kappa. But the Greek letter kappa and our letter K, they're identical. Okay, so if you call it K, that's fine. But if you really want to be nitpicky, that's actually the Greek letter kappa. But anyway, so this thing they call kappa and what we have previously called the refractive index, they serve the same function. What they do is it's a number that can be used to represent how much the speed of an electromagnetic wave slows down. It just turns out that this kappa that they talk about is actually n squared, or if you prefer, n is the square root of k. People who work with this kind of stuff day in, day out, sometimes it's a little easier if they work in terms of refractive indices, but other times it's a little bit easier if they work in terms of kappa. So, don't sweat it. They serve the same function, but just remember that they are not the same. N is the square root of kappa, or if you prefer, kappa is n squared. So make sure you keep that. So I hope you figured that out. Okay, so now that we've said that, let's talk about the answers to last night's homework. Again, I'm only putting up the ones that aren't already in the back of the book. So I'm trusting that you guys have already looked those up. So I'll pause for a second, give you a chance to look at those. Does anybody have any questions about them? Not seeing any questions. Okay. Okay, I do see a question. Number 18. So what about it? You want to go over how I did it? Okay, I can do that. Okay. Maybe I can do that. Maybe I can't. I'll get glasses out. Okay. Okay, so number 18 is saying, what is the frequency of an electromagnetic wave that has a wavelength of 2.2 times 10 to the negative 2? Okay, so what is the relationship between wavelength, frequency, and there's one other thing that comes into play. What is that? It's the speed of the wave. Remember the equation that about a month ago, I kept referring to it as our new favorite equation? Okay, so lambda equals V over F. Now in this case, if it's an electromagnetic wave, that V is actually C, the speed of light. Yes, very good. Okay, so all we need for question number 18 is just use that equation. So did I put down the wrong answer? How many of you, or well, did any of you get the same answer for number 18 that I got? I mean, I have made mistakes in the past. In fact, I'm all prepared just in case I messed up. I did bring the wig, but I don't think I messed up this time. You got a different answer, but you don't know what you did wrong. Well, okay, let me make sure I did it right. Okay, so we want to know the frequency. So lambda equals C over F. If I move the F up there and the lambda down there, so frequency is going to equal C over lambda. Okay, so C is 3 times 10 to the 8th. I'm going to divide that by the wavelength, which they say is, boy, I cannot see without my glasses. Okay, so they say it's 2.2 times 10 to the negative 2, and that is in meters. So I'm going to divide it by 2.2 E2, and I get, wait a minute.
I think the exponent's wrong. I think it's to the 10th, not to the 14th.
You know, Zach, I'm getting a different answer. Now, in my defense, this number that you see in the book here, I just copied it out of the book there, but I copied it wrong. Oh, rats. Tell you what, okay. I know it's only one mistake, but okay, that was bad. Okay, so yeah, so it should be 10 to the 10th. That's terrible. Okay, let me go in and fix that real quick here. Thank you for pointing that out, Zach. Okay. All right, are we good now, Zach? Let me, I got to move my windows. Okay. Okay. Oh, it wasn't you that said it? Oh, who was it? Okay, well, whoever was, oh, it was Zaid that said it. Okay, well, anyway, good job. Okay. Oh, now my glasses get caught in the wig. Okay. All right, so are we good now? All right, so I'm going to assume we're good and I'm going to move on. Okay, so new stuff. Uh, okay, first off, I want to show you this diagram. I want everybody to get familiar with this diagram because this is the way the light is quite often portrayed. And you guys hopefully remember that there's actually two components to a light wave. In fact, if we go down here, okay, so this is what I drew for you last time. So a light wave, or any type of electromagnetic wave for that matter, is actually a mixture of an electric component and a magnetic component. And this is basically what it looks like. But this is how it's quite often portrayed. So you see here the electric field, and notice how the electric field is perpendicular to the magnetic field. That's very important. Okay, but also don't be surprised if a lot of times you see only the electric component drawn. You'll see that a lot, especially if a teacher is up drawing on a board and doesn't really have time to draw it super right. What you're going to see is I'm just going to draw a sine wave, and I'm going to call it a light wave or an electromagnetic wave. But keep in mind that I'm really only drawing the electric part of the wave. There's actually a magnetic part to it too. So keep that in mind. That's really important. Okay, and also this chart right here. Okay, like I said before, but I'll say it again. Put a bookmark in your book on page 708, because when you take the test on next week, you will need this chart. I guarantee you'll need to reference this chart. Okay. Now, okay, so let's get into some interesting new stuff. Okay, so let's suppose that I want to take my antenna, and instead of emitting a radio wave, because that's what we talked about last time, right, was emitting a radio wave. But since we know now that radio and light are fundamentally the same thing, right? So would it not be possible to have our antenna emit light? The answer to that is yes, it would. So I want you guys to get out your calculators, and I want you to tell me how many times per second would we have to flip our battery if we want to emit light that has a wavelength that's right in the middle of the visible spectrum, the visible part of the spectrum. So let's say 530 nanometers. Okay, so I'm going to pause while you guys do some calculations. How many times per second would we have to flip that battery? So I'll wait while you guys do the math. And I'm not going to proceed until you've done the math. So we're going to be here for a long time unless somebody does some calculations.
I got 5.7 times 10 to the 14th.
And it looks like a lot of other people did as well. Okay, very good. All right, let's compare that with what I got. 5.7 times 10 to the 14th. Okay, very good. All right, so now let's think about that. Is it possible for us to do that? Okay, so let's think 10 to the 14th. Is that mega, giga, kilo, or what? Okay, so kilohertz is 10 to the third. And we human beings, for over 100 years, we have had electronics that can flip things back and forth to physically switch a battery, and actually, move the battery back and forth this fast, that would be not realistic. But electronically, we can essentially do the same thing. We can flip the signal. So for over 100 years, we've had the capability to do kilohertz. But that certainly isn't going to do the job for this. But for radio, on the radio, when they say that, when KSL comes on to say the 1160 on your AM dial, what they mean is 1160 kilohertz. Okay, any number that you hear on the AM dial, that's kilohertz. And so, like I say, for over 100 years, we've easily had the ability to flip the voltage at the kilohertz range. But in the early days, that was the best we could do. It wasn't until about 20 or so years later, about the time that your grandparents were being born, that we advanced the electronics to the point where we could flip things back and forth at the megahertz rates, okay? And then about the time that your parents were born, then we got into the electronics had advanced to the point where we could then flip things back and forth at the gigahertz range, okay? But in order to do visible light, we would need electronics that can flip things back and forth at the terahertz range, and actually hundreds of terahertz range. And we just don't have electronics that can do that right now. Maybe someday in the not too distant future we might. But actually there's some physics, some fundamental physics that's going to make that really, really hard. But basically right now, we just don't have electronics that are capable of flipping that voltage back and forth at the super high frequency that's needed to make an antenna that emits visible light. And yet, we have things that emit visible light. I mean, right over there in the corner, I've got a lamp, and that lamp is emitting visible light. So how is it that we're emitting visible light then? What is happening inside the light bulb of my lamp that is causing it to emit visible light if it's not a battery that we are flipping back and forth ourselves? Anybody want to pipe in with an answer? What is it that's happening inside a light bulb? Is it how much that it's heated up? Yes, Jaron, you're exactly right. Okay, so what's happening is inside that light bulb, we are sending electricity through there, and that thing is getting so incredibly hot that something very interesting is happening at the atomic level. So here's a picture that hopefully is not new to you. Hopefully Coach Miller talked about this in your chemistry class. Okay, so what you see here is it's an atom. Now this is a hydrogen atom, and the only reason I chose a hydrogen atom is because it's simpler, but it works for any atom. It doesn't have to be just hydrogen. Okay, so we've got these atoms that are so hot because we're running so much electricity through them that they're vibrating so much, they're so hot that this electron, which normally likes to stay down here in the lower shell, okay, because of the thermal excitation, it gets pushed up into a higher energy state than it likes to be, okay? Now, it's not going to stay there very long. In fact, only a tiny fraction of a second. But when it drops down, this is where it gets really interesting, okay? When this electron drops down, it wiggles like crazy. So when it's in the higher level state, it's relatively happy, okay? It's not jiggling a lot. And when it's in the lower energy state, it's fine, it's not jiggling. But when it jumps from one state to another, that electron just undergoes a super high frequency jiggle that is very much like flipping the battery back and forth, okay? And so it wiggles so much that remember, a moving electric field creates a changing magnetic field, and that creates an electric field, and so forth and so on. So it's that super high frequency jiggling of the electron as it jumps between energy levels that creates a magnetic field, which creates an electric field, which creates a magnetic field. So that is happening at the atomic level. Okay, so now, while we're talking about this brings up something that's very important, that's a very common misconception here about how things work in physics. Okay, so this picture that you see right here makes it look like it is what I call a classical wave. When I say classical wave, I mean a continuous wave, like the kind of waves that we've been dealing with up until now, sound waves and ocean waves and things like that. You've got this sine wave that pretty much just goes on forever. This picture makes it look like that is what a light wave is. Well, it's not completely true. In fact, it's not true. It's not true. That is not what happens to light wave. Because remember what's happening here. This electron has gotten bumped up into the high energy state, and it's relatively content there. I mean, I mean, it is going to want to jump down, so it's not completely content there, but it's not undergoing this strange wiggling, okay? So as long as the electron is up here in this higher state, it's not wiggling, therefore it's not emitting light. Now, during that brief burst or blip or whatever you want to call it, when it drops down, it emits a very brief burst. It jiggles, but only for a very brief time. And then once it gets down into the lower shell there, it stops jiggling, right? So the kind of wave that you're actually going to get is a wave that like you see in the lower right of the screen here. Okay, you got no wave for a while, and then all of a sudden you get a wave, and then you get no wave for a while again. What you see down here, that is what a light wave actually looks like. It's not really a wave, it's really a wave bundle or a wave blip or something like that, okay? Now, some people have unfortunately come to call this a wave particle. Okay. In fact, even on the picture that you see here, they have called it an energy particle, which is a horribly bad choice of words, because this has confused more people than almost anything that I can think of in the history of physics. People say, in fact, I've even heard some of you say it. You say that light is both a particle and a wave. And some people say, well, does that mean that sometimes it's a particle and then it changes into a wave for a while, and then it's a wave for a while, and then it changes back into a particle? And so the use of the word particle was an extremely unfortunate choice in the history of science. Because when you think of particle, you think like a little marble or something like that, and that is absolutely not what light is. Light is a wave, and it's not just a wave sometimes. It is always, always a wave. It's just not the kind of wave that people think of when they hear the word wave. Up here, where I've got the cursor right now, that is what people think of when they hear the word wave, and that's not the kind of wave the light is. Light is this kind of a wave. It's actually a whole bunch of them. I mean, this by itself is one photon. So my lamp over in the corner there, it's emitting gazillions of photons all at the same time. So you've got a whole bunch of these guys all crowded together. That's what light actually is, okay? So instead of calling it a particle, please don't ever do that. Let's call it a term that I like better. Like, what you could call it a wave bundle, you could call it a wave packet. If you want to call it a wave blip or a wave burp, hey, I'm okay with that. Just please don't call it a particle, even though that is what textbooks call it. I mean, even your textbook, they call it an energy particle. Okay, it's just really unfortunate choice of words in my opinion. So everybody good with that? So now you understand how light has properties that are kind of particle-like, even though it actually is a wave. Okay, so make sure you understand that. Okay, now, so let's do a little history lesson here. The history of radio. Okay, so remember how I said just a few minutes ago, I said that 100 years ago, we human beings, we had electronic equipment that could easily flip the voltage back and forth at the kilohertz range. Okay, so if you look on the diagram here, over here on the left, this band is AM radio. It's in the kilohertz range. And like I said before, if you ever hear somebody say the 1160 on the AM dial, what they mean is 1160 kilohertz. Any number that's on the AM dial is always kilohertz. Even though technically 1160, well, 1160 kilohertz is actually 1.6 megahertz, okay? So if you really want to be nitpicky, the AM radio band actually does extend up into the megahertz range, but only a little tiny bit. And so all of the numbers that they give are always in kilohertz. So if you're up above 1 megahertz, they don't call it 1.6 megahertz, they call it 1,600 kilohertz. Okay, so the early radio stations that they had 100 years ago, they were all in this range, okay? The highest frequency they had was 1,600. And that was the best they could do back in those days. Okay, then as time goes on, the electronics gets more and more advanced, more sophisticated. And so then we were able to flip the voltage back and forth at a much faster rate. So we're now up to like 10 to the 7th or so. And so then they came out with new radios that worked at higher frequencies, and they called these new radios shortwave radios. Because you guys know if lambda equals C over F, that means as lambda gets bigger, F gets smaller. Or conversely, as F gets bigger, lambda gets smaller, right? So these new higher frequency radios that they came up with, after the AM, okay, they were higher frequency, therefore lower wavelength, therefore they were called shortwave radios, okay? And then along came television. I hope you guys realize that television is really just radio. A television wave and a radio wave are exactly the same thing. It's just that the receiver and the transmitter have been set up so they can encode the radio signals with images. So they can take an image, encode it in a radio signal, send it through the air, and then your TV receives the radio signal. And then they've got the special equipment that can uncode the video signal that's hidden in the radio, okay? So TV is really just radio, okay? All right, so when the first TVs came along, they only had 6 channels. And they all worked in this range right up here. Not quite 10 to the 8th hertz, but in the upper 10 to the 7th hertz, that's where the TV stations were. And at that time, there were only 6 channels. But they only used 5 of them because they initially started out with 6 channels, but what they found was that the channel that they called channel 1, it got a lot of noise. And so people complained because the reception was really bad. So they quit using that. So back when my parents first bought their first TV, you could only get channels 2 through 6. That was it. That's all you could do. Okay, now time goes on and we get still better electronics because they can flip that back and forth faster. And so now we're getting to the point where we need some more radio stations because these original radio stations that they did way back, 100 years ago, if you look at this range of frequencies, there's only really room for about 100 different radio stations, to actually 106 if you do the math carefully. There's only enough room for a limited number of radio stations before one radio station starts interfering with another. And so people said, hey, we need more radio stations. Okay, so then they came and they said, okay, we'll give you some more radio frequencies that you can use. And so this is when FM radio came in. But FM and AM mean something different. FM radio stations, which by the way are measured now in megahertz. So when Milo says that his favorite radio station is 105.1 on the FM dial, anything that's on the FM is always going to be megahertz. Anything on the AM is going to be kilohertz. Okay, so FM came along much later than AM did, and so that's why it has the higher frequencies. But FM does not mean high frequency. FM means something different, which I will talk about in just a minute. I'm sure that some of you already know, but I'll talk about that in just a minute. Okay, so now the same problem happened with TV stations. People were complaining. They said, hey, look, 5 TV stations, that's crazy. We're going to go nuts. We need more TV stations. And by that time, electronics had advanced to the point where we could now do them at the higher frequencies. So these other TV stations came out, but they were at a higher frequency. And then now we're bumping up into the place where now we're into microwaves. Okay, but tell you what, let's go back and let's talk about AM and FM. Okay, so because FM radio stations are always at the megahertz band and AM radio stations are always in the kilohertz range, a lot of people think that that's what FM means, is high frequency. It doesn't. Now I know that some of you know this. Anybody want to take a minute and tell us what is the difference between FM and AM? FM radio and AM radio. Anybody want to speak up and say anything here? I see somebody's, okay. Hang on just a sec, my thing's not scrolling. Okay, is it based on how much it's heated up? Nope. Okay, Jaron, you are right. Amplitude modulation and frequency modulation. You are exactly right. Now, most of you are probably saying, huh, what does that mean? Okay, well, here's what it means. Okay, so back when radio was first invented, okay, the way that they approached it was they took this really high frequency, which is in the kilohertz, the high kilohertz, hundreds of kilohertz. So we've got this radio frequency, which we could broadcast if we want. But if we want it to carry sound, like let's say we've got a singer going ah, and we want to broadcast that singer, what we do is we have the singer sing into a microphone, and then we take the wave of the singer going ah, and we superimpose that on top of the high frequency radio wave. And so what you see here is where it's the loud part of the singer going ah, and here's where it's quiet, and here's where it's loud, and here's where it's quiet. So what we've done is we've taken this high frequency radio wave and we have modulated the signal, but what we've modulated is the amplitude of the signal. So the amplitude of the signal gets high, then the amplitude gets low, and then the amplitude gets high and the amplitude gets low. Okay, so then the receiver, it just listens, and when the amplitude is high, it goes high, and when the amplitude is low, it goes low. Okay, I mean it's kind of a duh, it's a no-brainer, it's an obvious way to do it, but it turns out that it's susceptible to noise. Okay, if you've got some other signal or some background noise, an amplitude modulation or a radio that you're listening to that's amplitude modulated, it's going to be a little bit noisy. The music's not going to be as clear and crisp as you would like it to be. So the first radio stations, that's what they did just because it was quick and simple. But by the time they got around to needing more radio stations and they introduced these higher frequency radio stations, they had many years of experience by then, and they realized that amplitude modulation was subject to noise. So they said, I wonder if there's a better way to do this, a way that would be less susceptible to noise. Okay, and it turns out there is, and it's called frequency modulation. Okay, so what they do here is, again, they have the singer sing into the microphone, but instead of modulating the signal according to its amplitude, what they do is they modulate the frequency. And the best way to explain that is to put these two side by side. Okay, so now up on the top here, you're seeing amplitude modulation, and the bottom is frequency modulation. So when you want the signal to be really high, what you do is you make the frequency be exactly what the radio is tuned to. So let's say 105.1, okay? So if we are receiving a signal that is exactly 105.1, we're gonna get a nice, strong, loud signal. But now over here, we want the signal to be quiet, okay? So instead of changing the amplitude, you'll notice the amplitude is always the same along here, right? But can you see what they've done with the frequency? They've purposely misadjusted the frequency just a little bit. So instead of 105.1, they make it be 105.2, okay, or maybe 105.0, okay. Now the radio can still pick it up, because the radio does have a little bit of range where it can pick it up. It doesn't have to be exactly 105.1, but if it goes very far off, it's going to come in with a lower, it's going to sound quieter, okay? So what you do is, when you want it to be loud, you make the frequency be exactly the carrier frequency. And when you want it to be a little bit softer, you make it so it's a little bit off from the carrier frequency, okay? And so the person listening is going to hear exactly what you want to hear. They're going to hear loud, soft, loud, soft, loud, soft, but they're going to hear it with less noise because, well, hopefully that makes sense. Okay, so give me a thumbs up. Does that make sense? Everybody understand the difference? Amplitude modulation, frequency modulation? Okay, good. Glad to see that. Okay, now let's talk. Okay, Bridget, you raised your hand again. Is that another mistake? I'll assume it is. Okay, now let's talk some actual applications here. Let's suppose that you live in a hilly region, okay? And so your radio transmitter is over here on the right. Your home is over here on the left, but you got a bunch of hills in between. Which radio stations do you think would give better reception? AM or FM?
FM.
Okay, so we got one vote for AM, we got one vote for FM. Anybody want to justify? So Jaron, you said AM. Do you want to explain why? And the voice that I heard, I think that sounded like Josh. You said FM. Do you want to justify why?
So I figure if AM you're amplifying the wave and you're making it not only go higher but also go lower. The wave that are really low will get interrupted by the hills with a really long amplitude. Whereas if you have the frequency, it's all going to be the same amplitude, so it won't have an issue traveling over the hills.
Okay, I hear where you're coming from, but there's a little bit of a misconception there. Tell you what, let's think of it this way. Okay, do you want this wave to diffract, or do you want it to not diffract? Remember, it's been a month now, or maybe even more, since we talked about diffraction. Here is a real world application of diffraction, very different from what we talked about. Okay, so if your house is down here in the valley and you got this wave, if this wave goes straight by, it's going to go right over your head and you're not going to hear it, right? So you see over here on the left how the wave is bending, it's diffracting. Do you see how in this particular application, diffraction is your friend? You want it to diffract, right? So remember the rule of thumb about diffraction. Do longer wavelengths diffract more, or do shorter wavelengths diffract more?
Generally shorter.
No, shorter waves diffract less.
Oh.
Longer waves diffract more. And by the way, this is something you might want to write down, because this is something that I personally think is very important. And there's a very high chance that there will be a test question next week asking about this. So everybody in your notebook, write it down and put a star by it. Longer wavelengths diffract more, shorter wavelengths diffract less. Okay, so in this situation right here, we want diffraction. Diffraction is a good thing in this case. So we want the radio stations that are going to have the longer wavelength. That means we want the radio stations that are going to have the lower frequency, because lower frequency means longer wavelength. Okay, so AM is what we want, and it has nothing to do with the amplitude modulation. We couldn't care less about whether the signal is amplitude modulated or frequency modulated. That's meaningless. But the AM radio stations, those are the ones that have the lower frequencies. That's what we want. Okay, so I hope that's clear. Okay, so now let's take it to the next step, next real world application of physics. Okay. Okay, so we talked about that. Okay, yeah, I forgot I put these slides in here. So there's the answers. Okay, so let's move on now. Physics close to my heart. You guys have heard me say many times, and you'll hear me say many times in the future, the best way to learn physics is to go sailing. So here's another great example of why it is that the best way to learn physics is to go sailing. Okay, so let's suppose that you are out on the ocean. All right, you're in boat A. You want to talk by radio to your friend who's over here in boat B. Okay, now at any given time there are thousands of boats out on the ocean. And so over here we have boats C and D, and they are probably talking to each other, right? And there's a limited number of frequencies, the limited number of channels, okay? So when you're talking to your friend over here, you and boat B are talking, you don't want the conversation from C and D to interfere with you, okay? So if you're gonna talk to boat B, and you don't want C and D to listen in, is it better to use high frequencies, or is it better to use low frequencies? I'm not going to go on until somebody types in an answer here. Okay, so Zaid is suggesting high frequencies. Somebody want to second that motion, or somebody want to oppose that motion? Okay, so Bridget is also agreeing that high frequencies are right. And so let's see. So yes, because remember, high frequency means short wavelength. Short wavelength means it does not diffract as much. I mean, it's going to diffract a little, not as much. Okay, so this situation that you see right here, that is what you want. Okay, you want the signal so that your friend can hear it, but for these guys who are over the horizon, they're out of your line of sight, you don't want them to be hearing you and you don't want to be hearing them. So high frequencies are definitely what you want for short range radio communication. Okay, but sometimes you do want to talk to a boat that is so far away that he's below the horizon. Okay, so in this case, I hope you agree that it's going to be the exact opposite now. Okay, here's a case where you do in fact want the radio wave to diffract. So that means that you do want the lower frequencies. Okay, so if you're on an ocean going boat, you want to have at least 2 radios on board. Now, it is possible to have one radio that does both. One radio that can do high frequencies and low frequencies. Well, they do in fact make radios like that. Okay, but typically, what they do is they have a set of radios that are optimized to work really well at very high frequencies. And in fact, that's what they call them. They call them VHF radios. Means very high frequency. So generally, when you go to buy a radio for a boat, you're going to buy one radio that's a VHF radio, very high frequency, and you're going to buy another radio that is a lower frequency radio that's intended for long distance communication. So you want to have these 2 different radios on your boat. Okay, now just FYI here, interesting, you might call this trivia. Personally, I don't think it's trivia. Okay, there is a group of laws that every country in the world has agreed, and it's called maritime law. So when you're out on the ocean, you're not really in any country, right? But they still have laws. Every country in the world has agreed that we will still enforce these laws even when you're out on the ocean where you're not really in any country. We call it maritime law. And one of those laws says that whenever you're out on the ocean, you must, by law, have your radio turned on, and you must have it tuned to the frequency of 156.8 megahertz. They call this channel 16. Can anybody think of a reason why they would have a law like this? Okay, so Joseph, I agree with you that the earth was flat. I thought so too, but you guys convinced me otherwise. Okay, so Yasin, what do you mean when you say storms? Why do you say for storms? Or does anybody else want to pop in with an answer? Why would there be a law that says any boat on the ocean has to be? Okay, so if somebody sees storms, they can alert the others. Okay, good. But not just storms. What? Okay, yeah, okay, Cohen, you got it exactly right here. So boats can broadcast a distress call. So, I mean, you guys have all seen Titanic, or at least if you haven't seen the movie, you certainly know about it, right? So this is actually the reason why they had this law. So the Titanic sunk in the middle of the night. Okay, they put out a distress call on the radio, and there were other boats within radio range who could have heard their call and could have come to their assistance in time to save the people so the people would not have died. But they didn't have their radio turned on. It was nighttime. They had gone to sleep. Okay. And so the Titanic put out a distress call. Nobody heard it until it was too late. And it sunk and a lot of people died. Okay. So since then, they have passed a law that you must have your radio turned on 24 hours a day, and you must have it turned to channel 16. Okay. Now, channel 16 is one of the very high frequency radio waves. Channel 16 is really only good for line of sight. So if you put out a distress call from boat A here, boat B will be able to hear it, but boats C and D, they will not be able to hear it because they're not in your line of sight. But that's okay because they're so far away that they probably wouldn't be able to get to you in time to help you anyway. I mean, if you're in distress, you need immediate help. So really it's the boats that are nearby. Those are the ones that you want to hear your distress call. Okay, and also there's another reason for why they do it this way. Channel 16 is not only used for distress calls, but it's also what they call the hailing frequency. So the way it works is if you want to call up boat B so that you guys can tell jokes or whatever, talk about how the great fish that you caught that afternoon, okay, what you do is you call him on channel 16, and he will of course be listening to it because by law he's required to. Okay, but then as soon as you make contact with each other, before you have your conversation, what you do is you say, okay, let's move our channel, or let's change to a different channel. Let's change to channel 16, or I'm sorry, channel 15, or maybe channel 17, or maybe channel 18. So what you do is you make contact on channel 16. You then switch to a different channel. You have your conversation on the other channel so that you keep channel 16 open for emergency use only. And then as soon as you're finished with the other conversation, then you put your radio back on channel 16 again. So that's the way it works. A little bit of sailing trivia for those of you who hopefully will someday go out sailing. Okay. And again, just sailing trivia. So typically the frequencies that are used, if you want to talk to somebody who's over the horizon, those frequencies are typically in the range between 2 megahertz and 30 megahertz, which is, I mean, that's still reasonably high. I mean, it's still megahertz, right? Not kilohertz, but it's nothing compared to 150 megahertz. So it is definitely lower frequency. So this is a bit of trivia that might possibly appear on a quiz or a test question. So I hope you guys are taking notes. And by the way, this is not in the book, but I think it's important enough that I might put it on the test. So I trust you guys are taking careful notes here. Okay, now if you really want to go crazy with physics and you want to do some really fun and cool physics, it is possible to bounce your radio waves off of the Earth's ionosphere. Okay, so you guys know that the sun is constantly bombarding the Earth with high frequency radiation. The upper atmosphere gets ionized. Remember we talked about ionizing radiation last time we met? So the electron gets stripped away. And so what you have is a whole bunch of molecules up in the atmosphere that have been ionized, and it turns out that they can bounce radio waves. So if you really want to get crazy about radio communication, you need to understand about how to skip things off the Earth's ionosphere. Are any of you guys by any chance ham radio operators? I remember one of you was talking about it. Okay, Dean, okay, good. So Dean, do you know about bouncing radio waves off the ionosphere? Did you, when you got your ham radio's license, did they ask questions about that on the test? And even if they didn't ask questions about it on the test, it's stuff you need to know about. Now, speaking of tests, I am not going to put questions on next week's test about it. Okay, so Dean knows a little bit about the theory, but you've never done it. It's actually very complicated theory. Because the Earth's ionosphere changes depending on whether it's daytime or nighttime, and there's different levels. I'm not going to go into details here. Just throw it out there as being really cool. But don't worry, on next week's test, I'm not going to ask about bouncing stuff off the ionosphere. But I certainly am going to ask questions about VHF radios versus lower frequencies, and I guarantee I'll ask questions about that. So make sure it's in your notes. Okay, new subject. Back when I got my first cell phone, back before you guys were even born, okay, I had a cell phone like the one that you see over here. It was a flip phone. I really miss it. It was a wonderful phone. It you fold it up nice and fit in my pocket. Wonderful. I really liked it, but it couldn't do the things that your smartphone could do. But it had this little nub on it. Anybody know the reason why the phone had the little nub on it? What is that little nub? Somebody needs to answer or else I'm not going to move on.
Is that like an antenna?
Yes, that's exactly right. Okay, it's an antenna. Okay, all right. So, and by the way, I know it's an hour, but we're going to go a little bit long. We're going to go for maybe another 10 minutes. Sorry about that. Okay, and what we're going to say might be on the test. So don't go away, or if you do go away, come back and watch the video, because what we're going to talk about is really important. In your book on page 706, they talk about the ideal length of an antenna. And what they say in here, I've highlighted in yellow, is that you will get the best reception if the length of your antenna is approximately 1/2 the wavelength of the wave that you are trying to listen to. okay? Now, I got to be honest and tell you that this is a rule of thumb that is not true in all cases because there are different types of antennas out there. Okay, and this rule you see here does not apply to all antennas, but it does apply to the most commonly used antennas. So I'm going to take this rule and I'm going to run with it. So if you have a radio and you want to get the best possible reception, okay, the way to do that is to make your antenna so that the length of that antenna is 1/2 of the wavelength of the radio that you want to receive. Okay, so here is a piece of information that I have taken from the practice test, which I'm not quite ready to give it out. I'm going to give it to you on Monday. Okay, but this is going to be at the top of your reference page. And if you look down the bottom here, you'll see that it tells you that cell phones they work in the range between about 820 to 850 megahertz. That's the range that your cell phones work at. Okay, so now if we have more time, I would ask you guys to calculate what is the ideal antenna length for a cell phone. But since we are getting short on time, here, I'll help you out. So what I've done is I've picked a frequency that's kind of in the middle of that range that I just told you, 850. I'm going to take everybody's new favorite equation, lambda equals C over F. Okay, so I know what F is, I know what C is, so I can calculate lambda is 36 centimeters. So using the book's rule of thumb that says the ideal antenna length is 1/2 of that, okay? So what I get then is that that the ideal antenna length for a cell phone is about 16 centimeters. And these old flip phones, they weren't long enough that they could fit a 16 centimeter antenna inside them. So they had to have a little nub, okay? You're right, Yasmin. You're right. 36 divided by 2 is 18. Okay, well, hey, I'm already wearing the wig. I mean, what more do you want me to do? Good catch, though. Thank you. Okay, so yeah, so 18 centimeters. Okay, okay, so it didn't fit inside the old flip phones. Now, the new style phones are bigger, which, I mean, it's good that it's bigger. Personally, it doesn't fit in my pocket very well, but oh well. But the new phones, they're all big enough that they don't need the nub because they can easily fit that 18 centimeter antenna inside them. So that's why the new cell phones don't have the little nub, but the old cell phone did. Okay. So what you see here might possibly be a question on either the test or the quiz. So make sure you understand this rule about how long an antenna needs to be. Okay, and so now let's just finish up here. So let's suppose you own a boat, and it's a boat that goes out on the ocean, and so you want an antenna that is optimized for the channel 16 because you know that's the channel you have to be listening to. So it's not very hard to do the math. You know the frequency, you know the speed of the wave. So it turns out that the ideal length for a VHF antenna is about 1 meter. Okay. On the other hand, if you want to talk to the boats that are really far away, then you want to use lower frequencies. So remember, the range for those is anywhere between about 2 megahertz and 30 megahertz. So I've just kind of picked one at random. I've picked 10 megahertz. So if we were to calculate what is the ideal antenna length for that radio, you'll get a very different number, 15 times longer than the antenna that you want for your VHF, okay? So how could we do this then? Okay, here's a picture of a sailboat, a very, very nice sailboat. Whoever owns that boat must be one very lucky person, okay? So if you look on the back of this boat here, right here where I've put this red circle, you'll see an antenna that is about 1 meter long. So which antenna is that? Is that my VHF radio or is that my long range radio? I need somebody to type something in. Which radio is that? Okay, that's my VHF radio, exactly. Okay, but I also need I need a long range radio too. And I need an antenna that's 15 meters long. Holy cow, 15 meters. How in the world am I going to get a 15-meter antenna on my boat? Aha, so Cohen is suggesting we use the mast. Okay, I like your thinking, Cohen, but what we're going to do instead of using the mast, you see all these wires? what these wires do, their purpose is to hold up the mast, okay? So what we're gonna do is we're gonna take this wire in the back that you see right there. It's a metal wire. It's a wonderful antenna, okay? So what I've done on my boat is I've hooked up so that my back wire here, which is called the back stay for those of you that are interested, okay? I've hooked it up so that that is my long range antenna, okay? Okay, so here's another photo of the same boat. And if you look way up here, you'll see some crazy guy has decided to climb all the way up to the top of the mast. And so here's a magnified view of this crazy guy up on the top of the mast there. So Yasin asking if it's better to be vertical. It turns out it's close enough to being vertical that it really doesn't matter. But anyway, so here's some guy up at the top of my mast working on something. And by the way, can anybody guess who that guy is up there? Okay, I'm sure you can. Yep, that's right. You got it. That's me. Okay, but if you look, can you see right here at the top of the mast? There's another one of those meter-long antennas. Oops, sorry. Let's see them. Okay, hang on. Okay, there we go. Okay, yeah, so up here at the top of the mast, there is another one of those meter-long antennas. So on my boat, and anybody who goes across the ocean, you should always have a backup. You know, you don't want to go sailing across oceans with just one VHF radio. You want to have a backup just in case, okay? So what you see here, this is actually my main antenna, and it's up on the top of the mast because the higher it is, the better, the longer range reception it's going to get. Okay, so you want to have two VHF radios, and you want to have two separate antennas for them, just in case, you know, for some reason, you know, some damage occurs to this antenna here. Okay, and then also you can see here that this now is, you can see the full length of my long range antenna right there. Okay, so it turns out that you can see now why it is that I say that the best way to learn physics is to go sailing. There really is a tremendous amount of physics in sailing. Okay, so today being Friday, I haven't given you an official homework assignment. I figure two assignments per week that's enough. I mean, I am a mean person, but I'm not that mean that I would give you 3. But I will, of course, give you a daily quiz. I need to do that because that's how I measure attendance. And today's daily quiz might be a little bit harder than a typical one because some of the stuff that we talked about today, I want to make sure that you guys understand that. So there will be a few questions on today's quiz that are a little bit harder than before, but not horribly so. So don't forget to take the daily quiz. Give me an hour and a half to get it posted because that's how long it takes to process the video. And very, very important, do not forget about next week's test. Everybody has to take it on Friday between, now I've said here between 1 and 2:30, but actually I'm going to extend it a little bit. I'm going to give it between 1 and 3. But everybody has to take the test at the same time. So make arrangements with your brothers and sisters and parents so that you have use of the computer and the internet at that time. Okay. So, any questions before we move on? Well, before we end is probably a better thing. Now, while I'm showing some pictures, I don't know if you guys would be interested. Oh, is that the final? No, Zach, that is not the final. We still got another month of school left. What do you mean final? Okay, so no, there is going to be one more after this. So anyway, while I'm showing you cool pictures of sailing, here's an interesting picture. Anybody recognize this person? This is somebody you all know. Anybody want to take a guess who that is? Yeah, right. No, it's not Carter Jensen. Come on, you guys know who this is. Somebody else, give it a shot. It is one of the teachers at Ames. It's not Carrie. Aho, yes, that's Miss Aho. Miss Aho has gone with me sailing, as have several Ames teachers. Senior Homer came with me, and a bunch of teachers who have now left Ames have come with me. So a lot of people have come with me. And so this is Miss Aho scuba diving with me one time when we went sailing. This is a picture of me taking a picture of her. There were several people in our group here. So while I was taking a picture of her, somebody else was taking a picture of me, okay? And here's another picture, which I do have to warn you, this one has been photoshopped. The shark was not there. Yeah, so those of you that got your hopes up, no, this one has been photoshopped, but this one has not. This is not a trick picture, you know, where the fish is really close and no. In this case, both me and the fish are the same distance away. This is what they call a whale shark, and he was huge. So I was snorkeling along and he came swimming along. That was very cool. So Anna's asking where I was. Well, this particular photo, I was in Indonesia when I took this one. But these other pictures up here, this one was in the Bahamas. This one was also in the Bahamas. The Bahamas is where I usually sail, but I have sailed down in Indonesia and other places as well. Here's, I caught dinner for the day. That one's, the hair might look photoshopped, but it's not. So this was our dinner. This, the mahi mahi, very good. Anna, how did you know that? Wow, I'm impressed. Yes, mahi mahi, that's what it is. And oh, they're delicious. They're really good. And here's some lobsters that I caught. I was down in the Caribbean at this time. So yeah, I don't want to spend too much time here. But yeah, if any of you guys ever get a chance to go sailing, you really should. It's very cool. Just, it's so beautiful, the fish and everything that you see. This is my daughter snorkeling. Just so beautiful, okay? And exciting. When you're out there on a windy day, the boat heels over and it's amazing. This is a picture that some of you may recognize. You know somebody in that picture, and it's not me. Yep, that's right. That's who it is. And in this picture right here, this is Lane here too. And yes, and that's Eve as well. That's Eve. Now this guy right here, that's not me. That's my son-in-law. That's my daughter's husband. But anyway, okay, enough with the pictures. Okay, so we are going to end the session unless anybody has any questions. So going once. Going, there, I gotta move a window around before I can close it. Okay, going once. Going twice. Okay, I'm gonna